The following video is for the energy objectives, so make sure that you have those printed off and ready to go. You should be reading along in your Princeton Review book. So the energy chapter is chapter 8. When you are done reading the chapter, you should also do the multiple choice questions at the end. The more practice, the better. And we'll start with number 1. So number 1 says to identify the source of energy on Earth and the process that transforms radiant energy into chemical energy. So the main source of energy on Earth is the sun. So go ahead and write the sun is the main source of energy. You should know, and we discussed earlier in the year, that there are other types of energy on Earth, but the main source is the sun. So we talked about energy from within the Earth. Some of that energy comes from the movement of the crustal plates, as well as the radiation given off from uranium and other radioactive materials within the Earth. And that's where we get our geothermal energy from. And we said that that process down at those hydrothermal vents in the ocean is called chemosynthesis. So there is another energy source on Earth, but the main one, if you had to pick, hopefully you would be able to identify that as the sun. The process by which energy is transformed from radiant energy into chemical energy is photosynthesis. So you probably know all about photosynthesis. I'm sure in biology you learn the ins and the outs of your whole reaction of photosynthesis. And if you look at the screen, you have the chemical equation for photosynthesis. So we start with carbon dioxide, so it says 6 molecules of carbon dioxide, 12 molecules of water. We need the radiant energy from the sun, and it's going to yield C6H12O6. So this is the chemical formula for glucose. It is the reason why photosynthesis happens. So this sugar right here is important to life, and this is moved on, and we're going to talk about cell respiration in a second. But this is the whole reason why we're kind of going through this process for this sugar. And then a plant is also going to give off oxygen, so that's why we like our plants and our trees, because they provide us with oxygen. And also there's going to be some transpiration from water, or from the leaves of the plant. So that's where we get our 6 molecules of water. So this is the chemical equation for photosynthesis. Like I said, even though you don't have to write this down, of course I want to contrast our cell respiration. So cell respiration is the process by which humans and animals and plants, they're actually going to break down this molecule, the C6H12O6, this glucose, and we're going to make it into our energy. So we have our glucose, and we breathe in oxygen, we need water to survive, and that's going to yield carbon dioxide, we breathe out CO2, water, and energy in the form of adenosine triphosphate, so ATP. And again, you probably remember the ins and the outs of this process from biology. You don't have to know all of that for the AP exam, but you should know the chemical equations, and you should have an idea of like the purpose of each one. So the whole point of cell respiration here is to get this energy so that we can breathe, move, reproduce, do everything that we need to do. Cogeneration, number 2. So it says to define cogeneration. If you remember the PowerPoint slide that I showed you in class, this is what it looks like. And cogeneration, the whole purpose of it, it makes perfect sense. It's like, why would you not do this? It's using one fuel input for multiple uses. So basically we're going to maybe burn coal, whatever it may be. So our fuel here could be burning coal. And we are going to, with that fuel, generate electricity. So don't forget, we pulverize the coal. We are going to heat it up. We're going to change water into steam that's going to turbine to produce electricity. And then that waste heat, whatever is left over, instead of just allowing that heat to come to a room temperature, a regular temperature, instead we're going to recover that heat and use it for another source of energy. So we're going to recover that waste heat, and we can use it for heating a building. So we can run a pipe through a building. We can produce more electricity. We can heat some water. If we're talking about industries, we can use it for other industrial processes. So the whole point is that we're using one fuel, And whatever waste is produced, we're going to use it again. So we're going to use it until that heat just dissipates, it runs out, and we cannot use it anymore. So it's an efficient use of fuel. Number 3 says to contrast electrostatic precipitators versus scrubbers. So let's see what our pictures look like. Well, first of all, you can see the definition here. A scrubber, which we've discussed so much, especially with our air pollution chapter, and we also talked about it with coal, is also known as a desulfurization system. So scrubbers are desulfurization systems. And we really discussed wet scrubbers. So if you look at the bottom left-hand corner of the slide, you can see like a little drawing of how a wet scrubber works. And basically what happens here is we have a flue gas, or a gas that's going to go out of a smokestack. And we fit it with this scrubber, this wet scrubber. And so water mixed with chemicals like lime, that's basic, it's going to spray down a liquid into the smokestack. And it's going to cause the sulfur and particulate matter to settle out. So because it's a liquid, it's going to adhere to tiny particles, so that's going to make that settle out. And the reaction with the chemicals in the water are going to cause sulfur oxides to precipitate out. And so then we're able to collect that, and then we have to dispose of it elsewhere. So it becomes a different type of disposal problem. So instead of going into the atmosphere, now we're going to collect it and possibly try and reuse it for another use if we can find something. Or it may just end up as a type of sludge that we have to dispose of. So this is what a scrubber does, and it says SOx and PM. Don't forget, SOx stands for sulfur oxides. It can be like sulfur dioxide, sulfur trioxide, and PM represents particulate matter. So that's what your scrubber is. An electrostatic precipitator is really specific for particulate matter. So electrostatic precipitators are filtration devices that help to remove fine particles using an electrostatic charge. Let's see if I have a picture. There we go. So this is what electrostatic precipitator kind of looks like. It can fit also into a smokestack, or these can also be separate. So I think on one of my slides I showed you a few electrostatic precipitators connected to a coal-fired power plant. So the air can be, or the gas that is polluted can be rerouted through the scrubbers. And so the way that this works is we have these particles that are going to go up through this grid right here. It says it's a negatively charged grid. And as it moves upward, it's going to adhere to positively plates on both sides of the scrubber. And then we're going to have some collecting plates that's going to collect those particles. So the point of an electrostatic precipitator is to reduce the amounts of particulate matter or particles. And then again, we have to dispose of that someplace else. Number 4, differentiate between the storage of low-level radioactive waste and high-level waste. Just to bring you back, and we're going to kind of hit on this again in a second, but we have radioactive waste, which when we talk about nuclear power, this is the #1 problem with nuclear power. So really it's the disposal of waste, and specifically high-level radioactive waste. So on the AP exam, if they have something, what is the #1 problem with nuclear power? Students, I'm sure, want to say, oh my God, first thing that you think of is explosions or catastrophic events. Yes, those are possibilities, but what faces our nuclear power plants day in, day out is trying to find a place to put the waste that's safe, because it can be radioactive for hundreds of years, depending on the half-life. So we have 2 categories. We have low-level radioactive waste and high-level radioactive waste. If you look here, low-level radioactive waste, it says here, it gives off small amounts of radiation. So this stuff can come from multiple places. It doesn't only have to be a nuclear power plant. It can come from medical facilities, industries. It could be from anything that deals with some levels of radiation. And some of the examples of actual, like, things that are radioactive could be paper, tools, clothing, anything that comes into contact with ionizing radiation. So here are some examples here. For the most part, low-level radioactive waste, we can allow it to become less radioactive and dispose of it just the way that we would normally dispose of it. We also have some places around the United States that accept low-level radioactive waste. So if we don't have a good storage site, a storage place on site, then it can be sent someplace else. And a lot of medical waste is actually incinerated. High-level radioactive waste. This is the stuff inside the nuclear core in a nuclear power plant that is giving off high amounts of radiation and most likely going to be radioactive for hundreds to possibly thousands of years. And so this is the concern. What do we do with this? Where do we put it to make sure that it's safe? And it includes here fuel rods, coolant fluids. You can think about the tiny little pellets of uranium dioxide. Anything in that core of the nuclear power plant, that is going to be highly radioactive. So currently, we don't have a place to put our high-level radioactive waste in the United States. And so it's kept at the reactor site at this time. If you remember, we talked about pools, so it can be kept on site in these pools where the waste is kind of lowered into these chemicals in the water, and it reduces the amount of radiation, and it reduces the probability of like a fire or some type of spark. And then in some areas, they have these above ground casks. So you can see the picture in the top right hand corner. And so these are very tall casks. They're well insulated. Many times they're heavily guarded, and they're at a nuclear power plant. And so the waste kind of just builds up into these casks. And then we're just kind of waiting for a permanent storage site. We talked about Yucca Mountain, and currently Yucca Mountain is not open. And so geologists and a lot of scientists believe that the best way to dispose of this waste is going to be burying it deep in the ground, some deep burial at some point in some place that we can identify that's not close to water tables, and it's not close to fault lines, and it's not close to volcanic activity. So it has to be a very specific place. So we're still waiting on that. All right, number three. Number three is super easy. I don't have a slide for it. It says, what three energy sources supply the majority of commercial energy today? And the answer is coal, oil, and natural gas. Those are the three for commercial energy today. Of those, if you had to name the number one energy source for commercial energy, that would be oil. So you can kind of circle oil, and that would be the number one, but these are the three that supply us with most of our commercial energy today. So commercial meaning like, and we're not talking about like biomass in a developing country. Okay, number 6, passive and active solar heating. We talked about this in chapter 13. This is part of our renewable energy chapter. And if you look on the screen, I have some passive solar heating here. And what you should really write down and know is that passive solar heating is going to utilize the greenhouse effect. So I kind of have it written there in cursive in very messy handwriting. But it's utilizing the greenhouse effect. That's how we're going to use passive solar heating. And it's mainly used for space heating, which means like heating up your home or heating up a greenhouse. So it's for space heating. We're not generating electricity from it, and we're not heating up water. So it's just to heat the inside of a home, basically. And if you look at the picture on the left, we looked at this picture, and this is showing you a home that's taking advantage of passive solar heating. And if you look, this house has to be in the northern hemisphere because you can see that this winter sun is lower in the sky, and so you would want, if this was your home in the wintertime and you want to take advantage of the greenhouse effect, you would want large windows facing the south. So all of that sun in the wintertime would be able to penetrate through the glass. That radiation would be trapped in your house, and it would basically heat up your home. So, and then you can see the overhang there, and it says overhang blocks the summer sun. And so even though it's called passive solar heating, it still can be used for cooling. So you may see like passive solar heating and cooling because that overhang there is going to block out the sun in the summertime, therefore keeping it cooler inside of the home. And on the right there, you can see that you could possibly build it onto your home here. You can build like a little greenhouse kind of thing, and in it you could have these drums or these barrels that are painted black that are filled with water or even oil. And what would happen here is that the sun's energy would penetrate through the glass, and then it would be absorbed by those drums or those dark colored barrels, and then the energy would radiate off, and then you would have a way of convection, basically taking that warm energy and warm heat and putting it into your home. So that's another example of passive solar heating. So passive solar heating, it's used for space heating, like heating up your home, and it utilizes the greenhouse effect. Active solar heating, and it's on the left here, don't look at the right, but on the left is active solar heating, and this is mainly to heat up water. So it also uses a series of devices or pumps in order to do this. And you may see this on the roof of someone's home, or you may have it where it heats up your pool water, it heats up the water in your house. And basically, you're going to have some type of solar collector, and you can see it right here. And this solar collector could be filled with water, it could be filled with oil because oil gets very hot. And the sun's radiant energy is going to heat up that water or that oil. It's going to bring it here to a heat exchanger where that heat is going to radiate from this pipe or this pipe, and then it's going to be transferred to this other pipe where we have a storage tank filled with maybe cool water, and it's going to absorb that heat energy. And then when you turn your faucet on or when you go in your pool and you put the heater on, you're going to have some warm water. So this is active solar heating. It uses a series of devices you can see here, and it's mainly used to heat water in buildings. On the right, I have a picture of a PV cell, and the reason why I like to put this on here is that students sometimes get confused with like solar heating and producing electricity. These are two separate things. So this PV cell on the right, this is showing you a way that we produce electricity. And so this is what you have in your calculator, and maybe you see them on the light posts when you're driving down the road. And this actually produces electricity. So nothing to do with heating up water. If you remember, we said that it has silicon, and the electrons from silicon are ripped off from the atom, and then we have a flow of electrons, which actually is electricity. So we're going to talk a little bit more about this when we contrast our renewable energy in a couple of slides. So yes, this is not active or passive solar heating. All right, the next one. Let's see here. Oh, here we go. Compare renewable and non-renewable energy. So just so that you know basically the difference here, and I'm sure you know the difference by now. But non-renewable energy on the left, it says it's a resource that cannot be replaced. And when I say cannot be replaced, we're really talking about like a short amount of time or a reasonable amount of time. So we can include all of our fossil fuels, so oil, coal, natural gas, and also I have this really pretty picture here because this is representing a mineral. So minerals are also non-renewable. So when we use this stuff up, it's going to take billions of years for it to come back, and it could be forming right now underneath the ground, but for the most part it's going to take too long and we're not going to have access to it. So it's non-renewable. Renewable energy or renewable things are things that can be replaced in a short amount of time. So here we have a picture of some trees, sun, some wind. So these are things that we're not going to run out of. So definitely not running out of the sun, because if we run out of the sun, then we're not going to be here. And the sun causes the wind. So the uneven heating of the earth is what we have, what wind is. And so we're going to have both of these. Trees. This is renewable if it's used sustainably. So there are some things that are considered renewable, like fresh water, trees, arable land, things like that, where if we're not careful with how we're using it, then it could potentially be non-renewable. But for the most part, we're going to keep our trees in our renewable category, because hopefully we're not going to cut down all of the trees on Earth at one time and then it take hundreds of years for them to grow back. Okay. So, if you look at that table that I gave you, it says non-renewable. I actually gave you this in the beginning of the school year, or when we went over our fossil fuels. So if you can dig that out and find it somewhere, if you're organized and you keep all of your stuff, then you can just copy it, or you could even just use the same one. So if not, then we're going to fill it in again. So just to go through our types of fossil fuels. To start here with coal. So our reserves for coal, and just to remind you the difference between a reserve and a resource is identified and extractable today. So we know where it's located and we can get it. And so a resource, just to remind you, is something that maybe has been identified, but currently it's not profitable to extract today. So it may be that we don't have the technology to extract it. It may not be economically worth to extract it. So we're talking about coal reserves here. And the top places where we have coal is the United States, Russia, and China. Those are your top 3 countries. What is it made of? Well, coal is actually different than oil and natural gas because it's from our swampy plant material that was converted into carbon-rich rock with heat and pressure. We extract it by the mining process, so concerns air pollution and mining. So we have to dig up the ground and we have to either surface mine or subsurface mine for this coal, and then we have to process it. If you ever have to discuss problems with mining, you could always mention acid mine drainage. So that's an environmental problem because when we have rocks that are exposed to water, many times the rocks contain sulfur. And so water and sulfur mixes, and it gives us like a acidic, orangey colored liquid that can seep from mines. So that's for mining. And also it gives us some air pollution. It's transported by trucks and trains. So we basically put it on a truck or a train and we transport it around the United States. And it's used to produce electricity. So remember that burning coal is to produce electricity. And the negative impacts here, you can think about the air pollution. I mean, of actually using the coal, you should think first thing, sulfur. Sulfur comes from burning coal, sulfur oxides. And you know that sulfur oxides are going to be a big contributor to acid rain. So sulfur is going to go into the atmosphere, it's going to combine with water, and we're going to have acid deposition. So sulfur causes acid rain. And then also don't forget that mercury comes from coal. So when we talk about bioaccumulation and biomagnification of mercury, that originates from coal. Let's see. How can its environmental impact be reduced? We could change fossil fuels, so we can instead burn natural gas because natural gas is cleaner. We could use better grades of coal, so we're going to talk about the grades of coal in a second. We can use air pollution control devices like scrubbers and electrostatic precipitators. We also discussed fluidized bed combustion. And mainly, if you ever had to write about this, you could say you can use alternative energy sources. So anything that's going to produce electricity, like some of the renewable ones where they are less polluting or they don't pollute at all. How many years do we have it for? So our reserves, we're looking at least 300 years. But as we're able to extract more coal, we probably have in resources close to 1,000 years. So this is not a fossil fuel that we're running out of. The reason why we don't want to use this anymore and we want to change to something else is because it's so dirty and so polluting. So of the 3 fossil fuels, this is the dirtiest one. And on the second bullet point here, you can see we have the different grades of coal. So we have anthracite, bituminous, subbituminous, and lignite. And it goes really from the left side of the page. So lignite's the least quality, so it's the most polluting, all the way to the best. So anthracite is the best. And remember that we use a lot of bituminous coal because we've largely exhausted the anthracite. So these are the types of coal that we have. And don't forget, I showed you anthracite in class, and it's so awesome. Okay. Our next one, oil. So oil and natural gas are both produced from microscopic organisms. So they were both produced as the microorganisms died in these swampy, marshy places. We had a lot of sediment that covered up these organisms. And over time, with heat and pressure, we end up with some hydrocarbons, and that's oil and natural gas. So where is it found? 65% of all of our reserves are found in the Middle East. You think like Saudi Arabia. I told you also that we have there's a decent amount in Venezuela. And it's extracted by mainly oil wells. So we have wells that are drilled deep down into the ground that are going to remove the oil and actually bring it to the surface. It's transported mainly by pipelines and tankers. It's used for transportation. So our oil is refined. If you remember, I showed you a distillation tower, and oil by different boiling points, it's heated up and it's changed into different products. So really, we use it for transportation. Obviously, it's in our gasoline. Some of the negative impacts or concerns. You could start with oil spills. That's always a concern. So we saw the BP oil spill, how damaging that was to the Gulf of Mexico. We're still dealing with things today. We're still seeing those pockets of oil come on shore. So oil spills, your book also talked about the Exxon Valdez oil spill. This is a major environmental problem. And air pollution, anytime you're burning really anything, you're going to release carbon dioxide. So CO2, and then from cars specifically, we said nitrogen oxides. And nitrogen oxides are going to also cause acid rain. So they're going to go into the atmosphere combined with water, and we're going to have acid rain and acid deposition. It can be impact can be reduced. Again, alternative energy sources. So we're going to talk about those in a second. Some renewable energy sources, things that we can power our cars and use instead of oil. Some of the, especially to produce electricity. We're going to see that on the next slide. And how we already did that one. How much longer do we have? So it's really hard to estimate because we're finding new oil deposits. We're having more technology. It's really, really hard. Now we have fracking, so it's hard to predict. BP came out last year, and they estimate that we have about 53 years at the current production rate. So for the most part, if they ask you a question about like the length of coal, oil, and natural gas, oil is the least. We have the least time with oil. So you can kind of remember that. In coal, we have the most. All right, natural gas. So like I said, natural gas is produced or made the same way that oil. So we have microscopic organisms and sedimentation. So sediment covers it, heat and pressure, and then we get our hydrocarbons. And you should know that natural gas is mainly methane. So CH4. So it's methane. And places that we have it, Russia and Kazakhstan. And methane, here you go. And the way that we extract it, we have gas wells, so we're able to extract it in that manner. We can transport it through pipelines. We talked about difficult transportation overseas. So if we have to import natural gas, it's really difficult if we have to put it on a boat and bring it over because it has to be kept at very, very cold temperatures in order to keep it, well, it's in a liquid form, then we actually have to gasify it, and then it has to be it is in a gas form, we have to liquefy it, and then when it gets to the United States, we have to regasify it. So we have to put it back into a gas. So it's difficult to do, and it makes it difficult to bring it overseas. What else do we have? It is used for electricity, so and also heating and cooking, so we can produce electricity. A lot of these power plants are now also adding in natural gas because it's cleaner. Impacts to the environment, like I said, it's the least polluting of the three. So if you had to pick one of these that are the best for the environment, it would have to be natural gas. It's explosive, so that could also be a problem. So I think we watched a video on fracking, and we saw that natural gas was coming up and seeping up from the wells, and so people were lighting their sinks, their water out of their sink on fire. So that's a problem. We can change to alternative energy sources to reduce the impact. And again, the years on this is kind of up in the air. Same thing with oil. Just know it's in the middle of coal and oil. Some of your review books say 50 years. Some of them say 75 years. Some of them say 100. So that just makes it very clear that we don't understand, or we don't know. All right, nuclear. So, least polluting. So only least polluting, water and CO2. So CO2 obviously is a pollutant though, greenhouse gas. All right, nuclear. So nuclear energy is also non-renewable because The fuel that we use is uranium, and uranium is a mineral, and we just said that minerals are not renewable. So minerals naturally form in the ground, and we are looking for uranium 235. So that's the type of uranium, or the isotope of uranium, that we use in conventional nuclear fission. Remember, this is a fission reaction, not a fusion. You can see your top countries here, Australia and Kazakhstan, and we have to mine for our uranium. It is transported, it's shipped in secure containers, and it really has to go to an enrichment facility, and then it's going to go to a nuclear reactor. So they're going to take that ore, and then they're going to remove the impurities. They're going to make little uranium dioxide pellets, and then those pellets need to go to a reactor or a nuclear power plant. The reason why we use it is for electricity. So we use it to produce electricity. We'll look at a nuclear power plant in a second. And the biggest impact and the biggest environmental problem, as I just stated a couple of slides ago, is the waste. So we have to deal with the waste products, and that's, a lot of them are going to be highly radioactive, and they're radioactive for thousands of years, and they have to be secure. So we have to make sure that they don't get in the wrong hands, and also that they're not going to pose a threat, that they're not going to be explosive. If you had to come up with a type of pollutant that goes into the atmosphere, I would say thermal pollution. Remember that tertiary circuit that removes the heat from within the reactor core, that's going to take the heat and put it into our environment. So thermal pollution in the water, if you remember, we talked about any power plant, but especially a nuclear power plant, when they release that waste from that tertiary loop, or that heated water, it's going to go to a surrounding bay or out to the ocean. And we said that the manatees like to congregate around that area because it's warmer water. But we also said that warm water, or thermal pollution, can reduce the dissolved oxygen in water. And so if you're going to lower the DO, it's going to be difficult for fish to survive. So they're not going to be able to really breathe and go through cell respiration, and then therefore they're going to die. So that could be a type of pollutant. Environmental impact. What could we do? Find a burial site, find places to put our highly radioactive waste. And then how much longer? Probably about 200 years at current consumption. So that's the amount that we have of uranium. And if you look at the screen, you can see the difference. We have U-235. We said that's used in conventional nuclear fission. U-238 is the most common. So, but it makes up most of our uranium ore. And plutonium-239 can be used in breeder nuclear fission. So there is an option where we could use U-238. But in conventional nuclear energy, what we use in the United States is uranium-235. Oh, and concerns. Nuclear waste, as I just said, and possibility of explosions and catastrophic events. Also, I almost forgot to tell you, power plants are decommissioned every 40 years. So they're licensed for 40 years. They can file an extension for another 20 years. But after 40 years, the nuclear power plant has to be broken apart. And the reason why is because we have all of these metals that can get corroded, and we're doing it for safety reasons. So that area of land has to either be guarded or decommissioned, and then we are going to have to build a new nuclear power plant. Just to remind you of how nuclear energy works, and I think I have another video for you on this, but we have a neutron you can see here. So this is in the reactor core. Thinking in a nuclear power plant, it's going to hit a uranium U-235 atom. It's going to eject some free neutrons, and they're going to hit another uranium-235, and this is going to happen over and over and over again. And so every time a uranium atom splits, energy is released, and that's the process of nuclear fission. So this is a chain reaction. We said that we have to use uranium-235 because it carries on the chain reaction. It is fissionable. So this is a process that happens inside the reactor core of a nuclear power plant. Oh, here's our nuclear power plant. So This is a pressurized water reactor, so a PWR, and this was the picture from your textbook. And you guys had to memorize the parts of a nuclear power plant, and I'll quickly go through this. I'm sorry, you can fast forward if you want. So we have this external part right here. This is called the containment building. Remember that this is concrete, probably 3 to 5 feet thick, and the point of it is to protect the reactor core and basically the primary and some of the secondary circuit here. So it's for protection. And we talked about Chernobyl, and in Chernobyl, they did not have, those nuclear reactors did not have containment buildings. So that was a flaw in their design. Inside the containment building, we have our reactor core. So you can see right here, this is the reactor core right here. This is where fission takes place. So this is actually where those neutrons are hitting the uranium atoms, the nuclei, and splitting them apart and releasing heat as energy. And here we have our fuel rods. There's like representing 3 fuel rods here. And we also have our control rods. And remember, when the control rods are lowered into the reactor core, the reaction stops. So the control rods are made of boron and cadmium and all these metals that absorb neutrons. And so it stops the reaction. And when their control rods are lifted out, then it allows the reactions to occur. So the neutrons are allowed to move freely, therefore hitting the nuclei of the atoms and releasing heat. In this primary circuit, which is orange, this water is under extreme pressure, so it's kept in a liquid state, and that's why it's a pressurized water reactor. And that water is going to move through the primary circuit, and it's missing pumps here. It should really have some pumps, but it's being pumped through here, and that heated water is going to overlap and be brought into what's called a steam generator. So here we have our steam generator, and we have our heat exchanger. You can see these coils here where the heat is going to transfer from the primary circuit to the secondary circuit. Remember that the water itself does not. So the water in the primary circuit stays in the primary circuit. It never mixes with the water in the secondary circuit. And everything here, again, is highly radioactive, even the water. So this water, the way that we dispose of it, it has to be made into a solid, and that process is called vitrification. So we take this water, make it into a solid, and then it's easier to store the solid than it is to store a liquid. Our secondary circuit is in the blue color right here. This is where we have water that is pumped to the steam generator. The water here changes into steam. The steam is going to turn a turbine connected to a generator that is going to produce electricity, and it's going to be sent to a grid. So this is where our electricity is actually made during the secondary circuit. And then that water, or that steam, is going to be condensed back into a liquid in this condenser, and then it's going to move back to the steam generator, and this is going to happen over and over and over again. So again, remember that the circuits don't mix. So the secondary water circuit does not mix with the tertiary water circuit with the green color. And then here we have water that comes in from for the tertiary circuit. It can come from a lake, it can come from the ocean, and it's brought in. And the heat from the secondary circuit is going to be transferred into the tertiary circuit. And that water is going to move out to either a cooling tower, or like I said, a lake, or it could be the ocean. And there is where we're going to have that heat released into the environment. So this is where you would have that thermal pollution. So water vapor is going to come out of here. If you were to see, like, looks like a cloud coming out of the power plant, it is just water vapor. And so that's how your nuclear power plant works. Quick reminder. Oh, breeder nuclear fission. So breeder nuclear fission, if you remember, is a type of nuclear fission that actually uses plutonium. We don't use breeder nuclear fission in the United States, but it's a good type of fission to use because the waste product can be reused almost in the reaction itself. So you see the plutonium-239, same idea here. Neutrons are going to hit the nucleus of the atom. We're going to eject some neutrons, and it's going to actually make uranium-238. And that uranium-238 can be made into plutonium-239. I know, it's crazy. So it's called breeder nuclear fission because it breeds more fuel, or it makes more fuel. But we don't like it in the United States because it's dangerous. It uses a different medium in that primary circuit, so it uses liquid sodium, which can be very reactive. And also, we kind of frown upon countries that are, or we basically don't want countries producing plutonium. Plutonium is a weapons grade material, and we don't want them using it because it can be used for nuclear bombs. Nuclear fusion, just to remind you what this is when we take the isotopes of hydrogen, so we have deuterium and tritium, and at very, very, very hot temperatures, we force them together, and we're able to get some energy from that. And this is the same process as the sun. So we do not produce electricity commercially yet with this. This is something that we are looking at for the future. And it's a really, really good option because we have abundant amounts of deuterium and tritium, and it produces no high-level radioactive waste. So the whole problem with fission is it produces so much radioactive waste. Fusion produces no high-level radioactive waste. So instead, we're going to have some low-level, and it's very promising for the future. So maybe we'll be using nuclear fusion soon. Oopsies. All right, looking at your renewable table. For your renewable resources, we have hydroelectric, so we'll start in the middle of your little table here. Some positives here: no pollution, it's cheap to operate. So remember, we always said for dams, because really we're using energy from flowing water, so that's your definition, but we're building dams, and dams are expensive to build, but they're cheap to maintain and to operate. So that was always like the saying. Problem with dams, so some of the negative impacts here, you're building a wall where you're stopping a river, and so it's going to alter the flow of the river. By doing that, you're going to destroy habitats, and we know that destruction of habitats is the #1 reason why animals become endangered and possibly extinct. And by building this dam, we talked about induced seismicity. So when we fill up the water behind the dam, known as a reservoir, that could cause like a minor little earthquake, which is probably not a good thing. We talked about fish ladders. So we said that fish, and like salmon, for example, they need to go upstream to spawn and to lay their eggs. And so if you build a dam, they can't get back upstream. So some major dams have built little fish ladders for them, or even fish elevators for them to get back upstream. What else can I tell you? Special feature at the bottom there. Most rivers have already been identified in the United States and around the world and have been dammed. So this isn't like the fastest growing renewable energy. It's we've already like identified our places, and it's already happening. So we're not really going to increase hydroelectric in the future. Okay. Wind. All right, your wind. Sorry, we're jumping around to the last column. Wind is caused by the uneven heating of the earth, which I said a couple of slides ago. So I think your book says something silly in the definition, like horizontal movements for wind, but you can define it however you want. We get kinetic energy, so energy of motion. Positives, no emissions. So when we use a wind turbine, there are no emissions. So we're not giving off like carbon dioxide, any type of emissions. It's clean. It's very clean. Some of the negatives, currently it's more expensive than using fossil fuels. So currently it's kind of expensive. You could always talk about the NIMBY attitude. So don't forget, NIMBY stands for not in my backyard. And even though we may think wind turbines are cool because we don't have a lot of them around here, most people don't think that they're very pretty. So they may be ugly, they're kind of loud. You have to be in a place that's windy. So if we're thinking about wind turbines in Florida, it would have to be off the shoreline and in the ocean. And we've said, like, if you have beachfront property and you've paid millions of dollars for your home, you don't want a wind turbine to be erected like right behind your house. It's like, how are you going to see the ocean? So NIMBY, and also it does kill birds. So the blades of the turbine actually do kill birds. So those are some of the negatives. And for your special feature, it is the fastest growing alternative energy source. So it's the fastest growing. Wind turbines are being put up all over. And even down here, there's not a lot of space down here, and it's also not very windy. But we have seen more of those horizontal wind turbines. Like I think I told you, Fort Lauderdale Beach, you can see them. And they're actually on the top of like hotels and stuff. So they look a little different, but we're getting better technology. And so we're able to harness like slower wind speeds. So it's pretty cool. All right. Geothermal. So I have multiple stars by geothermal here. And the reason why is because the energy is not from the sun. This is the energy from within the earth. So Earth's internal heat energy. So that could be your definition. Let's see here. Some positives. Little air pollution. So there's not really a lot of air pollution associated with geothermal energy. There's some sulfur that comes up. Think about it. Geothermal energy is the same heat that comes up at a hot spring. And if you've ever been to a hot spring, you know it smells like rotten eggs because of the sulfur. So there is some sulfur that's emitted into the atmosphere, but we could always use air pollution control devices like a scrubber. So little air pollution. Some of the negatives here, is it renewable? So that's kind of the question. We're really pumping up heated water out of the ground, and we're using it for electricity, and we're also using it for heating. Are we going to be able to continue to pump up water from deep within the earth forever and ever and ever? Is it going to be renewable? So that's kind of a question there. And it can damage ecosystems. So if you're just digging down into the ground, you're going to possibly damage or fragment a habitat. So that could also be an issue there. And for your special feature for that one, you could put not derived from the sun, and you can also put that Iceland uses a lot of geothermal energy. Biomass. So biomass is, let's see, between on your table, hydroelectric and wind. And it's organic material derived from living or recently living organisms. And when we talk about biomass, we usually talk about like wood. And we should think that less developed countries, this is what they use. So for your special feature, one of the main forms of energy in less developed countries. So they cut down the trees and they burn the wood and they produce heat and they cook their food with it. And so that's biomass. Positives. It's renewable if it's used sustainably. There we go back to the trees. If we are using it sustainably, meaning that we don't cut down all of the trees. We have to be careful. We're seeing trees disappear, and we talked about the Amazon and slash and burn and how it's happening way too fast. And so that's a problem. But it's renewable if we are planting trees. Negatives, kind of along those lines. It leads to deforestation. If we really wanted to use fuels from biomass like ethanol, it would require a lot of land. We would need a lot of pesticides, a lot of fertilizers, a lot of fossil fuels. So it is renewable, but it's probably not the best renewable energy source. But like I said, they use it in developing countries. Solar. So this is for sure renewable. There's no question about that. Solar is radiant energy from the sun, which we talked about a second ago, and this is mainly for PV cells, so photovoltaic cells. What we talked about before was using the sun's energy in order to produce heat. So this is really to produce electricity. And specifically, photovoltaic cells or PV cells, like I said, the ones that you have in your calculator. All right. So our positives, it is limitless. We are going to have the sun's radiant energy forever. And if we don't, we're not going to be here, so it won't matter. So limitless supply. Really little to no environmental impact. These solar panels that we can use are not giving off greenhouse gases. I mean, it's made of something, so obviously there's production of it, but it's not giving off greenhouse gases. So little environmental impact. The negatives, it's still inefficient, so it's not producing a lot of electricity, so it's inefficient, and they can be expensive to maintain over a period of time. Special feature, can produce electrons with the PV cells, and I think that's all I got for you for solar. Math. Okay, so exciting. So, I'll go back really quick. If you have not done the math and you want to give it a try, press pause now so that you don't know the answers right away. But here are the answers to those few math questions. It's like A through F, and it also shows you how to do it. So press pause. Okay. The math. So we love math and love dimensional analysis. And I think this is a really good example, and it also shows you how you can do the math. But here are your answers. So A is 500 gallons per year. B is $1,750 per year. C is 10,000 pounds of carbon dioxide per year. D is 400 gallons per year. And then we have, it says 100 gallons per year saved. E is $350 per year, and F is 2,000 pounds of CO2 per year. So hopefully you got those right. And if you have questions, you can come see me. But math. We love math. You also have two half-life problems on your paper. And excuse me. I'll just give you the answers for those because I don't have it written out. But number 1 is 12.5 grams, and number 2 is 7.2 seconds. So we'll do some more half-life in class too. I hope you enjoy this video. I'm sorry I talked so much and it took so long. But you guys are going to rock